Okie dokie, we are reading. Page 22 and 23. We're still in section 1, theory of heat. Okay, first word in the period is transfer. Convection and conduction require some form of matter to be the transmitting medium. The Earth does not experience the total heat of the sun because heat transferred by radiation diminishes by the inverse of the square of the distance traveled. In practical terms, this means that every time the distance is doubled, the heat intensity decreases by a factor of 4. If you hold your hand close to an incandescent light bulb, for example, you feel the heat's intensity. But if you move your hand twice the distance away, you will feel only 1/4 of the heat intensity. Figure 1.12. The intensity of the radiant heat diminishes by the square of the distance. Got it at 1 foot. A certain amount of heat is sensed at a distance of 1 foot. Now it's at 2 feet. Twice the distance. The amount of heat sensed is 1/4 of the original amount. Keep in mind that because of the inverse square of the distance rule, radiant heat does not transfer the actual temperature or heat quantity value. If it did, the Earth would be as hot as the sun. Electric heaters that glow red hot are practical examples of radiant heat. The red hot electric heater coil radiates heat into the room. It does not heat the air, but it warms the solid objects that the heat rays encounter. Any heater that glows has the same effect. 1.7. Sensible heat. Heat level or heat intensity can readily be measured when it changes the temperature of a substance. Remember the example of changing 1 pound of water from 70 degrees Fahrenheit to 71 degrees Fahrenheit. This change in the heat level can be measured with a thermometer. When a change of temperature occurs, we know that the level of heat or heat intensity has changed. This is called sensible heat. 1.8. Latent heat. Not all changes in heat content result in a change of temperature. Some heat transfers result in a change of state with no temperature change. Such heat transfers are referred to as latent or hidden heat transfers. An example of a latent heat transfer is any additional heat that is added to water while it is boiling in an open container. Once water is brought to the boiling point, adding more heat only makes it boil faster. It does not raise the temperature of the water. Figure 1.13. Adding 3 times as much heat only causes the water to boil faster. The water does not increase in temperature. There are 3 other terms that are important to understand when referring to latent heat transfers. Latent heat of vaporization, latent heat of condensation, and latent heat of fusion. Latent heat of vaporization is the amount of heat energy in BTU/pounds required to change a substance into vapor. For example, the latent heat of vaporization for water at atmospheric conditions is 970.3 BTU/pounds. For ease of calculation, we often round the value to 970 BTU/pounds. This means that if we have 1 pound of water at 212 degrees Fahrenheit, that we want to change to 1 pound of steam at 212 degrees Fahrenheit, we would need to add 970 BTUs of heat energy to change the water. Latent heat of condensation is the amount of heat energy in BTU/pounds required to change a vapor into a liquid. This is, in effect, the opposite of latent heat of vaporization. For example, the latent heat of condensation for steam at atmospheric conditions is 973 BTUs a pound. If we had 1 pound of steam at 212 degrees Fahrenheit that we wanted to change to 1 pound of water at 212 degrees Fahrenheit, we would need to remove 970 BTUs of heat energy from the steam. Latent heat of fusion is the amount of heat energy needed to change the state of a substance from a solid to a liquid or from a liquid to a solid. The latent heat of fusion for water is 144 BTUs a pound. If we had 1 pound of ice at 32 degrees Fahrenheit under atmospheric conditions, we would have to add 144 BTUs of heat energy to the ice in order to melt it. If, on the other hand, we had 1 pound of water at 32 degrees Fahrenheit under atmospheric conditions, we would have to remove 144 BTUs of heat energy from the water in order to freeze it. The following example describes the sensible heat and latent heat characteristics of 1 pound of water at standard atmospheric pressure from 0 degrees Fahrenheit through the temperature range to above the boiling point. In the chart in figure 1.14, in figure 1.14, notice that temperature is plotted on the vertical axis, and the amount of heat energy added to the water/ice/steam throughout the example is plotted along the horizontal axis, along the bottom of the chart. Okay, figure 1.14. The heat/temperature graph for 1 pound of water at atmospheric pressure explains how water responds to heat. An increase in the sensible heat causes a rise in temperature. An increase in latent heat causes a change of state, for example, from solid ice to liquid water. Yeah, so sensible heat, you can see it. It's always going up and over, but latent heat is invisible. It's just a flat horizontal line. Since no heat is added to the start of this example, the heat content scale starts at 0.1 at 0 BTUs a pound. As heat is added, the temperature will rise, except during latent heat or hidden heat processes. The following statement should help you to understand the chart. 1. Water is in the form of ice at 0.1, where the example starts. Remember that 0.1 is not absolute zero. 0.1 represents ice at 0 degrees Fahrenheit and is used as a starting point. Since no heat has been added to the ice at 0.1, the heat content, as read on the heat content scale along the horizontal axis, is 0. From 0.1 to 0.2, 16 BTUs of heat energy has been added to the ice, as can be seen in the diagram. After the addition of this heat, the temperature of the ice is now 32 degrees Fahrenheit. This is a sensible heat transfer because there was a measurable temperature change. Since it took 16 BTUs of heat energy to raise the temperature of the ice from 0 degrees Fahrenheit to 32 degrees Fahrenheit, we can conclude that it takes only 0.5 BTUs of heat energy to raise the temperature of 1 pound of ice 1 degree Fahrenheit. 3. When 0.2 is reached, the temperature of the ice is 32 degrees Fahrenheit. This is the highest temperature at which ice can exist. If more heat is added, it will be a latent heat and the ice will start to melt. Because this is a latent heat transfer, the temperature of the ice will not increase. Adding 144 BTU of heat will change the 1 pound of ice to 1 pound of water at 32 degrees Fahrenheit.